Let's solve a second turbine problem. This one will make an air turbine. Air expands through a turbine operating at steady state. At the inlet, P1 is 150 psia, T1 is 1400 degrees R, and at the exit, P2 is 14.8 psia, T2 is 700 degrees R. The mass flow rate of air entering the turbine is 11 pounds mass per second, and 50,000 BTUs per hour of energy is rejected by heat transfer. Neglecting kinetic and potential energy effects, determine the power developed in horsepower. So let's lay out our storyboard as always. We have a schematic showing that air is flowing through a turbine, enters at state 1, exits at state 2, and it expands as it goes through the turbine blades, which cause the shaft to rotate. Now we are given pressure and temperature at both the inlet and the exit. We're also given the mass flow rate and the heat transfer. Now Q dot is minus 65,000 BTUs an hour, and that is because the heat transfer is transferring energy from the system to its surroundings, so it will be negative. Let's plot this on a TB diagram. This is air, it's a gaseous phase, and the initial conditions are 150 psi and 1400 degree R. Now it expands going through the turbine so that it's going to exit at a higher specific volume than it had at the inlet, and it expands to a lower pressure and lower temperature. So that's what our TV diagram looks like. We're going to model this as an open system operating at steady state. We'll ignore kinetic and potential energy effects as being insignificant. And we're going to treat the air as an ideal gas. Let's calculate the power output of this turbine in horsepower. This is a fairly simple problem. We can solve this problem with just the open system energy balance. We know that dEdt is 0 because it's operating at steady state, and that's equal to Q dot minus W dot plus M dot times the change in enthalpy plus the change in kinetic energy plus the change in potential energy. Now we're ignoring potential and kinetic energy effects, and so we can rearrange this equation and solve for the power output. It's just Q dot plus M dot times the change in enthalpy. So we need to get the enthalpy values from the air table, and because we know the temperature at both states, we can do that directly. We find that the enthalpy at state 1 is 342.9 BTUs per pound mass, and the enthalpy at state 2 is 167.56 BTUs per pound mass. So now we have everything we need. We can plug this into our expression. It's calculator ready now. We have the power output is minus 65,000 BTUs per hour, which I'm going to convert to seconds here. And then we have the mass flow rate, 11.0 pounds mass per second. And then we have our two enthalpy terms. And that will give us the power output is 1,910.68 BTUs per second. But we were asked to find the output in horsepower. So I'm going to convert seconds to hours. There's 3,600 seconds in an hour. And there's 2545 BTUs per hour in a horsepower. Calculate that the power output of this turbine is surprisingly large at 2703 horsepower.